My name is Murray Rudman. I'm going to be the lecturer for the second part of ENG1060, where we're going to be looking at numerical methods. And for some reason, that is displaying completely crazily on the screen here. I'm not too sure why that is. It was fine 2 minutes ago. You can find me, and it's a little bit hard to see from here, but the PDF that's up on Moodle should be fine. I'm in Building 82. Building 82 is that new silver and black building right next to the multi-storey car park. I'm on the second floor in room 218. And if you come into that building and you climb up to the second floor, you will see that it's got security access. Your student cards, you should just swipe them on the little thing next to the door. You should have access to that building to come and see lecturers who sit in there. Okay? If you don't for some reason, then you better go and talk to someone at the engineering front desk saying that you have a lecturer who sits in that building, New Horizons building, and that you don't have access. So you should be able to just come in. But my consultation hours at the moment are appearing there appropriately. At the moment, they're looking like Tuesday 1 till 2, Wednesday 12 till 1, and Friday 10 to 11. Okay? I'm going to really encourage people, if they're struggling with concepts in this unit or with anything in this unit, that you come up in my consultation hours and you speak to me about it. Okay? There's no point leaving things until the end when you just haven't understood anything. Any attempt to catch up at the end of the semester will be pretty much futile. So keep on top of things and come and see me. Okay, so let's have a little bit of a look at what you've been doing over the first 6 weeks of this course. You've been learning, I hope, to program. And so let's just have a show of hands. Who actually thinks that they're starting to get the hang of MATLAB? So about half of you. So that means there's about half of you that aren't really getting the hang of MATLAB. Okay, I'm going to strongly advise you that you've got mid-semester break coming up next week, that you put a bit of effort into doing it, because if you don't, the rest of this unit is going to become increasingly difficult. So hopefully what you've done is you've obviously had an introduction to the MATLAB basics, opening up the window, starting it up, understanding a little bit about matrices and vectors and how to operate on matrices and vectors. You should know about the built-in functions, obvious things like sine and cosine, tangent, log, all of those kinds of things, and also how to plot functions, both functions that you create and data that you might read in, or data that you might create, vectors or matrices you might create within a MATLAB script. You should know about M-files. M-files basically is just a lazy way, in my opinion, of talking about a file that's got some MATLAB code inside it. Okay, now that can be actually a script file which actually runs, or it can be a function file that actually just has those little bits of MATLAB code that do one specific task. And then you can call those function files within other bits of MATLAB code. And you can nest these things many, many layers deep. You should know about I/O, input and output, how to read things in, how to write things out. Some of those really important constructs like if-else statements, switches, in other words, controlling the logic of your program, whether you do this thing or that thing there. Yeah, no, sorry, I actually called back and said that I'd fixed the problem. So they didn't call you. I'm sorry about that. Thanks, mate. One of the most important concepts in all of programming, not just in MATLAB, is this idea of loops, doing the same thing many, many times. And you will have learnt 2 loop constructs in MATLAB, a for loop and a while loop. And you need to know the difference, and you need to really understand when you would use one over the others, over the other kind of construct. You should also know the fact that you can nest these loops. You can put loops inside loops inside loops. And you're going to need to do that in some of the things that we do in the unit, in the rest of the unit. And hopefully by now you should have also figured out some of the limitations of MATLAB and some of the difficulties. Okay, so that's in the past. Let's look to the future. Whoops. A little comment at the bottom there. You now have the basics you need to program solutions to real problems. And we're going to be looking at solutions to real problems. They're going to be simple problems, but the ideas that you're going to take away from looking at these simple problems will allow you then to tackle progressively more complicated problems, more complex problems. Okay, for the rest of the course, the next 6 weeks, Part 2 is all about using, or Part B it should be, is all about using your MATLAB programming, the skills that you've picked up in the first part of the course, to develop various different kinds of numerical tools. And what I mean by a numerical tool is a little bit of MATLAB code that does a particular task. It might integrate a function, it might solve a differential equation, it might find the root of an equation, it might calculate a Fourier series to approximate some data, it might fit a curve to some data that you've measured. Each of these different little things we're going to call, or I'm going to call, a numerical tool. And these are, as engineers, these are the tools of your trade. These are the kinds of things that you will need to use when you go out there and get a job. Now, in lots of engineering companies, of course, they've got all kinds of amazing software that can do incredibly complicated things. So why do you need to learn these simple tools? Well, in actual fact, you can't always use those really complicated bits of software because of the nature of the problem that you're looking at. It might be data that's come off from a spreadsheet somewhere, and you need to do something with it. You're not going to be able to squeeze that into any of the bits of software that you've got. You're going to have to write your own little bit of script and actually solve what in a particular problem it is. That's not just in your job, you're also going to have to do the same kinds of things in the rest of your degree. So one of the things I really want to try and get across is that don't think, oh, at the end of ENG1060 I won't have to worry about MATLAB any longer. You will have to worry about MATLAB in other units in your degree. Okay, and that's more so the case depending on which discipline of engineering you end up heading into. But don't think MATLAB's dispensable and disposable and you don't need to worry about it at the end of semester. You'll need to continue using it. Okay, so if you put the effort in up front, then it becomes second nature and you don't have to think about it. Once you get proficient, it's just like using a pen. It's like typing into a Word document. You don't even have to think twice about it. So all of the numerical methods, all of these tools of the trade that we're going to be looking at here are common to not just engineering, but all branches of science. So biological sciences, chemical sciences, physical sciences, all disciplines, all different parts of engineering, social sciences, all of these things play a role across a huge broad spectrum of endeavour. Okay, and you are going to need to use some of these things again in other parts of your degree. So what you do here, you might actually be able to use in a second year unit. And I should know because I teach the second year unit and I look at my lecture, the students in the second year unit, and I say, well, wait a second, you did this in ENG1060, why don't you know it? I'm basically giving you something for nothing here, but either the students have forgotten it or they never really understood it in the first place, so they forego that opportunity to get some easy marks. So get them now while you can. I'm going to make a bold statement, and that is that Engineering 1060 is brutally cumulative. So what do I mean by that? I mean that what you've done in the first part of this course is absolutely essential for the second part. So what we learn from week to week is going to be taken on into subsequent weeks. Okay, and that's particularly the case when you look at what you've done in the first part of the course. You cannot do the second part of the course without programming in MATLAB. You have to program in MATLAB. Without that, you'll get nowhere. So successful completion of the first part successful completion of the second part, part B, depends on understanding part A and programming in it. So if you're still having problems with that, still struggling with the programming part, figure out what it is that you're having problems with and come and see me, okay? Because it's not rocket science. It's just a matter of getting familiar with a few simple things and programming will be easy. Trust me, I have been through the same thing myself. Okay, so, well, you must understand the basics of programming before you can use programming to solve engineering problems. I think that's a bit of a motherhood statement, really. You can't do something until you can do it. But there is a key to being successful in programming. What do you think that is? Anyone? Ah, very good. Practice. But it's not practice once. It's practice many times. Okay, and it's the same with anything really. You've got to practice it to get good at it, but programming is particularly like that because to begin with it's an alien and a foreign way of thinking about things. So you've got to get your mind around thinking about things in an incredibly logical way, because the computer will always do exactly what you tell it to do. And if you tell it to do something stupid, it'll do something stupid. Okay, and I'm sure you've all found that already in the programming that you've done to date. Okay, so you've got to get your mind thinking incredibly sharply, in an incredibly logical way, to even get the simplest bit of MATLAB programming working. But once you sort of trained your mind to do that, things come easier. Okay, so what we're going to sort of do today is look at a particular kind of problem. But first of all, I want to introduce this idea of a mathematical model and of dependent variables and independent variables. I'm hoping that you probably know this, but just in case you don't, when I say a mathematical model in this unit, in fact in most of engineering, a mathematical model here expresses the essential features of some kind of system, and in our case it's usually a physical system, in mathematical terms. So we're writing equations to describe the real world. And one thing you should probably always remember is that those equations aren't the real world, they're some description of it. They're more rigorous and more mathematical than a verbal description, but a verbal description gives you a different kind of information. But we're going to be talking about things that look like equations, and that's going to be our mathematical model. Now, the simplest kind of mathematical model can be written like this. Our dependent variable, it might be pressure, it might be temperature, it might be stress, it might be concentration, is equal to some function of our independent variables. And so the distinction here between dependent and independent variables is that this one depends on those ones. That's why it's called dependent. Okay? This is the one that will take values that are determined by these. And the independent variables can span whatever range they can span. So you might have a function that's a function of x, y, z and time. So the spatial dimensions go from minus infinity to plus infinity, and time goes from now forever. Okay? They can range over whatever values they can, but the dependent variable will only take the values that this function here allows it to take. So this idea of dependent and independent variables is quite important in mathematical modelling. So we're going to have a look at an example. And we're going to look at an example of determining the terminal velocity of a free-falling bungee jumper. Okay, now the key thing here is he's free-falling. In other words, his bungee cord hasn't begun to get any tension in yet. In actual fact, for what we're going to do here, let's just take away the bungee cord. He's a guy who's jumped off a building. Okay, so he's going to have a few forces on him. So we need to figure out how fast he's going to go. What's his terminal velocity? And we're going to start off doing this with Newton's second law. Newton's second law of motion, I'm hoping you all remember this, is that the sum of the forces on a body, on an object, is equal to the object's mass times its acceleration. So what do you think, trying to figure out what the terminal velocity is, what's the equation going to look like? Terminal velocity, what does that mean? Acceleration equals zero. In other words, he's not going faster, he's not going slower. The jumper's going at a steady rate. So the acceleration is going to be zero. Dead right. Okay. Acceleration is the derivative of velocity. A equals dv dt. I hope you all know that one. So Newton's second law just becomes the sum of the forces on the body equals the mass of the body multiplied by dv dt. We divide through by the mass, and we come up with a very simple equation. Again, it's not rocket science. dv dt is equal to the sum of the forces divided by the mass of the body, the mass of the object. So, what forces have we got on this bungee jumper who's jumped off the bridge without a rope? Well, there's going to be two. It's actually pretty simple. First one is this downward force due to gravity. It's something that's accelerating him continually downwards. And for the point of this little exercise here, we're going to say downwards is positive and upwards is negative. Okay, we didn't have to do that, but that's just the way we're defining things here. So the downward force, or the drag force, is equal to mass times gravity. The upward force is the force due to air resistance. So as he's going down, the air's rushing past him, and as he goes faster and faster, the force gets larger and larger. In fact, the force goes like some kind of drag coefficient, don't need to know what that is yet, multiplied by the velocity squared. Okay, so as the velocity goes up, the force on the bungee jumper goes up much more rapidly than linearly. So the sum of the forces is just mg minus c v squared. Remember, downwards is positive. And so if we combine Newton's second law, which we've rewritten like that, with the forces, just substitute this right-hand side into this thing here, we end up with a differential equation that looks like dv dt is equal to g minus c v squared on m. Okay, so the velocity, we actually see that the velocity appears on both sides of this equation. So it's not just a simple matter of integrating this with respect to time, because we can't. The v's on both sides. Now, I'm not too sure whereabouts you're up to an ENG1060, 1090 I think it is, 1091. You should know how to solve this. You don't need to solve it for this unit, I hasten to add, but you should know how to solve it, and I suggest that you do it. But you can actually find an analytic solution to this equation. It's moderately straightforward. We can write the velocity as a function of time is equal to this coefficient here multiplied by the hyperbolic tangent of this thing here. Okay, so what this means is we know what gravity is, provided we know the mass and provided we know the drag coefficient, then we know that the velocity as a function of time. So we put in any time there, we can figure out what his velocity is. Okay, that's pretty straightforward. What I've actually done here is, and we can do this quite easily, we can say, well, in actual fact, let's imagine we don't know what the mass is, or let's say the mass might even change. We can actually write this function v as a function of mass and time. We can arbitrarily choose to do that. It doesn't make any difference. If we know the mass, we just put the mass in. If we don't know the mass, or we want to see how this function varies as a function of mass, we just add that as an extra variable. In actual fact, if we wanted to say, well, I'm only interested in the velocity at time 10 seconds, I want to see how this velocity at 10 seconds is a function of the mass, of a different weight or different mass bungee jumpers. Okay, so that's just nomenclature, basically. The key thing here is a variable that can be expressed as a function like this. V is a function of these things here, is said to be an explicit form or an explicit function for V. In other words, once I've got everything I need to know, I can calculate V straight away. Okay? It's explicit. I don't need to do anything tricky. I just plug the values into the right-hand side and I know what the velocity is. So if I know the mass, know the drag coefficient, I know what time I'm interested in, I can calculate the velocity. It's just straightforward. But there's other questions you might want to ask yourself. And let's ask ourselves this question. If I wanted a bungee jumper to have a particular velocity at a particular time, what mass must that jumper have in order to attain that? So now, in actual fact, the unknown thing is the mass. We don't know what the mass is equal to. We know what time we want it at, we know how fast we want it to be going, but we don't know how to do that. So what we want to do is we want to write this thing, try and take this thing here as m is equal to some function of stuff. Okay, now if you've got something like y equals sine x, it's really easy to do. Just x is equal to the inverse sine of y. You can invert an equation like that in a very straightforward way. Y is equal to x squared, x is equal to the square root of y. But we've got something like this now. It looks somewhat more complex. And in actual fact, it turns out, and you can have a go at doing this if you really feel inclined, it's not possible. You can't actually, because we got the square root of m here, and we've got hyperbolic tangent of 1 on the square root of m there. There's no way of decoupling these things and getting it right, being able to write this expression as m equals an explicit function. So as written here, this is an explicit function for velocity, but it's an implicit function for mass. It depends what way we want to look at this equation. So after all of that hoo-ha, variables that cannot be expressed explicitly are said to be implicit. So if we go back to this equation here, we can't write it explicitly, m is equal to something, but somewhere contained in this thing is an implicit description of that function m. You kind of with me? I hope so. Okay, so our design problem, remember, was we've got a time, we've got a velocity we want this bungee jumper to be falling at. What mass does this person have to do? How are we going to find a solution to this problem? Well, we take our equation, which is this equation here, and we just subtract v from both sides. 0 is equal to our function minus v. Doesn't seem to be doing very much. But we now say, okay, let's let a new function, f of m, equal this thing here, which is this original right-hand side minus the velocity. So we've now got a function of m, which depends on the velocity and the time and all of those things as well. We can actually plot this. If we know what the time is, we know what the velocity is, we can actually put in different values of m, and we'll come up with a function. Okay? So our problem becomes one of finding the root of this equation here. In other words, when this function of m crosses the axis, the x-axis, when its value is 0. So if we choose small values of m, presumably it's going to be negative. We choose large values of m, presumably it's going to be positive, or vice versa. But there'll be some point where this crosses the x-axis. In other words, when f is equal to 0. And that's what we're trying to do. So the whole process, and this kind of thing appears really frequently in engineering problems, obviously not bungee jumpers, but other things, where you've got to write some kind of implicit equation like this, and you've got to figure out what value of a particular parameter will give this thing equal to 0. Okay, and that value of m then also represents the mass that solves our design problem that we've got here. So if we choose the right value of m, then we'll know that the velocity is equal to this thing here, and we will have solved our problem. So, how are we actually going to find the root of this equation? We've already said that analytic methods for this particular case are too complicated, and in actual fact, in the real kinds of problems you're likely to get in the real world, you're not going to even have equations like this. They're going to be things that are outputs of other complicated programs. You won't be able to even write them as a function. Okay, they're going to be much more complex than this. So analytic methods are impossible. In actual fact, you could use a graphical method. So here's our function f of m. Let's choose different values of m from 50 to 200 kilograms, and we get this curve that looks like this. And we can see that this crosses the axis at around about 135 kilograms for the particular values of time and velocity that were chosen here. But this is not really very precise. You kind of like, you're looking at this graph and you're saying, well, it's about 130, 135. That doesn't really give you the answer that you want. So what we're going to do, unsurprisingly, because this is a unit in numerical methods, is design a numerical method to find the root of this equation. Now, you could actually use trial and error. In other words, you could just throw in values of the mass, and gradually you get closer and closer and closer. It's not a very effective way of doing things. It's certainly not an efficient way of doing things, because you'll make lots and lots of guesses, but it's not something you can automate. The guess making comes out of your head. You choose the next value. You need some kind of process by which you can rationally make a decision on what value you need to choose next, and that's what root finding is all about. So, root finding methods, we've already crossed out the graphical analytic method. We're going to look at numerical methods. There are two broad classes of root finding methods. The first are called bracketing methods, and we're going to have a look at bracketing methods in the rest of the lecture. The other class of methods are called open methods, and the reason for that will become pretty clear. Under the bracketing methods, there's two main ones, a bisection and the method of false position. Under open methods, there are three methods which are actually very, very similar. Newton-Raphson, secant method, and the modified secant method. Okay, so we're going to look at these two today, and next lecture we're going to look at those three there. So bisection is probably the simplest way you could imagine of doing this, and it's almost a little bit like your random guess-making process. A little bit. So let's have a look at our function f of x. It's doing something like this. The first step in the bisection method is to choose two values of x, one of which you know the function lies on one side of the axis, and one of which you know the function lies on the opposite side of the axis. So, in this case here, let's choose x lower and x upper to be 0.03 and 0.12. Okay. One of the key things about the bisection method is you have to know approximately where the function changes sign. You can't just be given a function and choose any values, unless you chose incredibly large values, but then this method would take an incredibly long time to converge, and it wouldn't necessarily converge on the right root if it has multiple roots. So one of the weaknesses of the bisection method is you've got to have some kind of knowledge and understanding of where the root is so that you can make sensible choices for the lower and the upper bounds. And usually the best way of doing this is to plot the function. Okay, so we know, well, okay, it's going to be crossing the axis at about 0.06, so let's choose something on one side and something on the other side that are far enough apart that we know that the function changes sign across the axis. It could go from negative to positive or from positive to negative. It doesn't matter which. So we've now chosen our interval that we know contains the root. And the way we know it contains the root is we calculate the function value at those two values of x. And we look, do they have different signs? So we know that we've chosen a sensible lower and upper bound. The first step in the bisection method, unsurprisingly perhaps, is to calculate the midpoint, xr. It's just half of xl plus xu, given by this formula down here. We're calling it xr because it's our approximation to the root. It's not actually the root, unless you're incredibly lucky and you happen to get it first time round, but it's your approximation to where the root lies. Okay? So we're now saying, okay, we've got our lower bound and our upper bound. We've chosen a guess for our root, which is right in the middle. The next question we have to ask is, well, we know that unless we're incredibly lucky, that the root is not going to be here. It's either going to lie in this domain, subdomain, or in this subdomain here. Okay, which one is it in? Is it going to be this one here or that one there? How do you think you go about checking this one out? Excuse me? Into? Yep, and so then you've got a function value at xr, and what else do you need to do? You're on the right track. You need to compare it to the function value at either the left side or the right side, okay? It's going to have the same sign as one of them and the opposite sign to the other one. So, you know, to begin with, knowing that you've chosen a good enough interval means that they have to have opposite signs. Well, the same goes now for your middle guess. You calculate the function value there, and then you say, does it have the same sign as the left one or the same sign as the right one? Okay, so clearly, one of four things can happen. It can either be, if we look at, say, x lower and xr being on the right-hand side here, it's either going to be negative, positive, positive, negative, or positive, positive, or negative, negative. There's only four choices, all right? You can't do anything else. Okay? If the estimate of the root in the middle, the midpoint, has the same side as the left-hand side, then we know that it must appear in the right-hand side, and vice versa. So the root lies in the subinterval where the sign changes. Okay, and checking for the subinterval can be actually carried out mathematically quite simply without having to do any complicated logic. You basically look at the function value, and we can choose the lower bound or the upper bound. It doesn't matter which. What I've done here is I've chosen the lower bound, but you can equally choose the upper bound if you choose. The logic's just swapped around. If the function value at the lower bound times the function value at our midpoint guess have the same sign, then it means the root's got to be on the right-hand side. Otherwise, it's got to be on the left-hand side. So you don't need to check those four cases for sign. You just need to multiply the two function values together. If that function value is negative, it means they have opposite sign. That function value is, the product of the function values is negative, they have opposite sign. If the product of those function values is positive, it means that they've got the same sign. It doesn't matter whether it's positive or negative. We just know that they're on the same side, so the root has to be in the opposite thing. So you can see that the logic behind this is actually pretty simple. Then what we do, once we've figured out that, okay, the root either lies on the right-hand side or the root lies on the left-hand side, we then change, in this case here, we change the lower bound to become our midpoint, and we repeat the iteration. Likewise, if we figured out that the lower subinterval is where the root now lies, we change the upper bound to be the midpoint. So what we're doing, we're starting off with a great big long domain. We're saying, okay, what's the midpoint value? The midpoint value, the midpoint value is here. Function value there is going to be negative, and the function value there is going to be positive, so we know that the root then lies in this half. So we then move the lower bound to the midpoint, and and we calculate a new midpoint. We then do the same thing. Well, the function value at the midpoint here is positive. So then we shift the upper bound down to the midpoint. And we check it again, calculate the midpoint. We go, and so we keep on going until eventually we get closer and closer to the root. The bisection method, provided you start off with values that do bracket the root, the bisection method is guaranteed to always converge. You will always get an answer out of the midpoint method. One of the problems is it does it slowly, and if that function call is actually really expensive, it might be the output of another big computation that you've got to do. This actually takes a long time to do and can be incredibly expensive. So there are much faster ways, but this way is guaranteed to get the answer. So how are we going to put this into a bit of MATLAB code? So we're going to start off writing pseudocode, or what in computer science terms would be called an algorithm. An algorithm is just the logic behind what you're going to do. Okay, it's a way of describing the process without getting into the details of the code. So the algorithm is, first of all, well, the very first thing here should actually be a step 0. Step 0 is calculate a lower bound and an upper bound, but let's assume that we've got those and we know that they're good. The loop that we're going to have to go into is calculate the midpoint, calculate the function values at, in our case we've chosen the midpoint and the lower bound, but you could choose the midpoint and the upper bound if you wanted to, it doesn't matter. Then check which subinterval our root's in by multiplying these two function values together and seeing what the sign is. Then changing the lower or upper bound to be the midpoint and repeating this step until our function value at the midpoint is close enough to 0. So let's expand on that just a little bit. So we're getting a little bit more like MATLAB now. We're sort of taking it one step at a time. So calculating the midpoint, that's what we did before. Calculate the function value at the center point. This is the bit here where we actually check the subinterval for the root. So we multiply the two function values, the lower one and the midpoint value together. If that is greater than 0, it means that the lower value and the midpoint have the same sign, so therefore the loop is in the upper part. So the lower limit now becomes the midpoint, so xl equals xr, and we reevaluate the function at the new lower limit so we can then go back into this loop. If this wasn't the case, in other words, the product of this was less than 0, then the upper limit, xu, becomes equal to xr. We don't actually need to calculate the function value at xr because we never need it. Okay, it's only the function value at the midpoint and the lower point that we're using here. And I've said it, I'll say it again, you could actually swap this around and use the upper limit if you wanted to. There's nothing special about the lower limit. So again, go through this loop until f of x, the function value at the midpoint, is close enough to 0. Okay, and the way in which we do that, I was actually going to ask this question, but I've already stolen my answer. You need to use a while loop here. You can't use a for loop because you don't know how many iterations of this thing you're going to need to do. I mean, you could use a for loop with a huge counter and then break out of it once you've found the root, but that's a really clumsy way of doing things. It's poor programming practice. Okay? You need to use a while loop. Really, really important for all of these things that we're going to be talking about here. If we're checking if something is close enough to 0, we need to use absolute value. Because the number we get out might be minus 10 to the minus 50. Well, that's pretty damn close to 0, right? But if you just check this thing here as being... I'm going to mess myself up here, but you need to use the absolute value, otherwise you might just get closer and closer and you'll be coming up from the negative side. Okay. So, while this is greater than the precision, if you have a negative value here, then that will never be greater than the precision that you choose. So you'll find the answer straight away, even for a large value of negative. Okay. So here's our pseudo-ken. While the absolute value of our function value is greater than whatever precision we choose, 10 to the minus 2, 10 to the minus 6, 10 to the minus 10, we do this loop. Calculate the midpoint, calculate the function value at the midpoint, do this check here, change the values, and go through the loop. So this pseudocode here, I'm hoping that people can look at this and say, yeah, that'd be pretty easy to program in MATLAB. Because this is almost MATLAB code here. Okay, it's so close to MATLAB. So we started off with something a little bit generic and a bit described in words, and step by step we've moved to something that looks much closer to code that you might want to write. Okay, so just think to yourselves, you don't need to answer any questions, but think to yourselves, do I think that I could take this description here and write a MATLAB function that calculated a root of a function? Because that's the kind of thing that you're going to have to do in the rest of this unit. Okay? If you don't think your MATLAB, if you've got no clue as to where to even begin doing this, you've got to come and see me. Okay? And come and see me not with, oh, I don't understand. Come and see me with what you don't understand, exactly what it is that you're having troubles with. Okay? Because you need to be able to do that without really even thinking. Of course, with all of these things, you usually need to initialize things. You can't just jump into this loop because you've got to figure out what various things are. And so the first thing you need to do, because we're always using the function value at the lower limit, and we jump into this loop here, comparing these two things, but we've never actually calculated it. So we need to calculate the function value at the lower limit to begin with. Otherwise, when we get into this if test here, this function value will be 0, and the product won't be greater than 0. In fact, we'll actually keep on doing. You'll jump into this. After one iteration, you'll probably get to the precision. So you need to calculate the function value at the left-hand side. We also need to know what the function value is at the midpoint in this computation here. We need to know what the function value is at the midpoint in this while loop, in this while test up here. If this is set initially to be 0, then this loop will never execute. Okay? So to begin with, unless we set this thing equal to some number that's bigger than our precision, doesn't have to be 1, it can be anything, but it's got to be bigger than our precision, we'll never actually ever execute this loop. So it's not just the loop in here, you've got to think about every step of the way. So when you do, especially when you're doing tests for the first time in a loop, you've got to make sure that what it is you're testing against isn't going to make you jump out of the loop before you've ever even executed it. So those are some of the traps that you've got to be careful of. Okay, so based on that pseudocode that we've got there, it's pretty easy, and I hope it's going to be pretty easy for you to write a general purpose function for the bisection method. What kind of inputs and outputs do you think we're going to need in such a function? So we want to write this as a function, an M file which is a function. We don't want to just put this in a script file. We want to be able to call this. What are we going to need to pass into the function? What does it need to know? Let's just go back. Let's go back to this loop here. We want to be able to use this function for this root finding function for any mathematical function at all.
The upper and lower bounds.
Yeah, upper and lower bounds. Dead right. Those are two things that we need.
Probably need a function as well.
You need a function as well. Absolutely right. Otherwise, what are you finding the root of? Yep. So that's 3 of the 4 things we need to pass in. Precision is the other one. Okay. So you look at this and you think, okay, what is this function going to need? It's going to need a lower bound, an upper bound, the function that we're actually trying to find the root of, and the precision to which we're prepared to accept that the answer is good enough. And the output, well, the output is going to be the root. Okay, it's going to be a simple one. So our function header is going to look something like this. Function root is equal to bisection function lower bound, upper bound, precision. Okay, and you can kind of see that. It's not great, but is that better? Yeah? Okay, well, look, I don't really like being in the dark, but I'll have to do that. I can barely see this on my screen, to be perfectly honest. But this is the bit of MATLAB code that does this. You can see it's not very many lines long. Okay? So, bisection, function, lower, upper bound, and precision. We calculate the function value at the left-hand side. We put it in a variable called fxl. We just set fxr at the midpoint equal to something to begin with, because we don't want to jump out of this while loop before we've even executed it, we then go through that while loop. So this bit of code here looks, oops, where are we? Looks almost identical to this. There's such a close correspondence. And you also need to do something to print out the results of your iteration as well. Okay, you can be trying that out in your next lab session. So let's have a look at how this thing works. So what we want to do is we want to determine the mass of a bungee jumper who's going to have a velocity of 36 meters a second after 4 seconds of free falling. We're going to assume that the drag coefficient is 0.25, and we need to know that the acceleration due to gravity is 9.81, and we want to achieve a precision of 0.5%. Okay, so there's our function m. We've got these values here. Now this, I've got to say, this is a pretty, in my opinion, a pretty clunky way of writing this function handle. Okay, because you've actually hard-coded everything in except the mass. You can do it that way, and there's nothing wrong with it. You get the right answer. But if I say, in actual fact, the drag coefficient's 0.3, it's not 0.25, you've actually then got to go in and change the 0.25s to 0.3, and you might miss one of them. If you left them in here as either parameters in your function handle, which you could do, although then you need to pass those into the root finding function as well, so that's probably why it's been written this way. But in general, if you can make these things general so that you can change the parameters with a single change of parameter, that's better programming style. The problem is, of course, when you need to pass this into another routine, it doesn't necessarily know what those parameters are. So let's have a look at this in MATLAB, if it's going to work for me. Okay, so all my scripts have disappeared. Oh, here they are. Okay, so here's the, no, you can't really see that very well. Okay, so that's the MATLAB script that we're just talking about there. If we then actually just see that, okay, we've set all these parameters equal to various things in here. We've set the function equal to this function handle equal to that. We then pass this into bisection, which is the function we just wrote. And if we run that, we actually see we get the root right there, and the value, and this screen is way too small. The mass is actually 142.57 kilograms. And if we actually run this thing here, which animates this whole process. So, okay, here we go. This is the function across from 50 to 200. We've chosen a lower bound of 50, upper bound of 200. Our midpoint is here. The next guess, we choose it's this upper limit here. The next guess, the root is going to be this midpoint here. And then we can see that in actual fact, this actually comes very, very close to the root, but it's not quite close enough. So the bound then goes there, the midpoint becomes there, the midpoint becomes there. We're then sort of starting to hone in very closely on the root. And then finally, after about 6 iterations, we hone in on the root. So the process of the bisection method is incredibly simple. Okay, there's almost nothing there that you need to, there's no real mathematics there. You just need to know that the product of 2 positive numbers is positive and the product of 2 negative numbers is also positive, and vice, product of a positive and a negative is always negative. You need to use that in your root to figure out where you shift your bounds to and which bound you shift, the left bound, the lower bound, or the upper bound. So really, this is just a problem of logic more than anything else. But it's getting your head into that space where you can think clearly and logically and precisely. That's usually where the difficult thing comes in. Okay, I said there were 2 different kinds of bracketing methods. The first one was the bisection method. The next one is called the method of false position, or the false position method. In actual fact, these 2 methods are incredibly similar. And conceptually, there's only one difference between them. Okay, but the process of actually using this method is identical to the bisection method. Instead of choosing a midpoint, we're going to choose a guess for the root, xr, which is given by this formula here. Now this looks complex and crazy, and where did it come from? In actual fact, it's got a very simple explanation. Again, with the false position method, you need to choose a bracket, you need to choose a lower and upper bound that bracket the root. If you don't do that, this won't work. You then draw a chord or a straight line between the function value at the lower point and the function value at the upper point, and wherever this line crosses the x-axis, that's our new guess for the root. And so you should go away and convince yourself that this formula here is actually correct for calculating this crossing point here. Okay, so you can see that unless the function happens to be a straight line, this is not going to give you the root, but it's going to get closer by and large to where you want to be. So we take this as our next guess. Down here, this will still say as the lower bound, sorry. We then draw a chord. Whoops, we're going to draw a chord that will go from this point up to here again. And again, we're actually going to, in this particular example, always come in from the lower bound. Unless we get really close, perhaps. So this is the method of false position. We can see the first guess is this point here, so we move the lower bound to here. We then draw another curve, and according to this plot here, the bound is very close, just here. We then choose that as the lower bound, it comes to here. At this point here, then it's the upper bound that comes down, and eventually we hone in again on the root. The method of false position is somewhat faster than bisection. Okay? So the problem that I'm going to give to you is to write a function for the method of false position. Okay? What are the inputs required? Are they any different to the bisection method? Someone going to say yes or no? It's got to be identical, right? You need a lower bound, or you need a function. What function you're trying to find the root of? You need a lower bound, you need an upper bound, and you need a precision. In every other sense, this method is the same as bisection. It's just the way in which you choose your next guess is different. Okay, so your function header is going to look something like that, and you're actually going to get a chance to try this one out in your next next laboratory. So we've just covered two bracketing methods, bisection and false position. These are called bracketing methods because you have to initially choose values of the lower and upper bound that bracket the root. If you don't do that, it's not going to work. By and large, higher precision means you need to take more iterations, but you get a better estimate of the true value of the root. Both of these methods, though, converge slowly compared to other ones, and there's just some functions here where if you don't choose your lower and upper bound correctly, or if you don't know what the function is doing, you can have problems with. So in this case here, for example, you've actually got two roots. And it may be that this is the root that you want to find for whatever reason, and not this one here, but it looks like this is the one that you might find first. Likewise, you might have multiple roots. You might have something like a tangent, which actually has this kind of weird singularity at the centre point here. Okay, that's it for today.